what we have discussed up to now. All forgot when you are coming to the campus. Yeah. Okay. So in the last class we have done few numericals, but before that we have talked about the flat rolling, okay, and the analysis. So initially we derived the draft, okay, the initial thickness minus the final thickness, and then we derived the volume initial, whatever the volume equal to the final volume. For example, T0 W0 L0 equal to TF WF and then also we derived the reduction, okay, reduction equal to whatever the draft we found and divided by the initial thickness, right? Then also we talked about the forward slip. This is Vf minus Vr by Vr. Then the strain, this one we derived. And then also the flow or the average flow stress. Then also the draft maximum, Dmax. That also we derived mu square into R. Mu is the friction and R is the radius of the roll, right? Then finally we talked about the force. And this is Yf bar into width into the L or the length of contact. And then also L we derived R into D to the power 1 by 2. Okay, or maybe root over R into T0 minus TF. Based on this, we have done 2-3 numericals, right? But only we have missed one thing, that angle. Okay, so today we will talk about the angle of contact, and also we will understand what is the angle of bite. Okay, almost these are same, but at least we have to define somewhere where you are calling this is angle of contact and where this is calling as angle of bite. So this is the schematic diagram. You can just see here. Okay, so you know already we have, for example, we are normally talking about two roll initially. Okay, so this is the basic fundamental. We have two rolls here, and whatever the raw material or the sheet you are passing from the left hand side and is going toward right hand side. And also we have discussed maybe few classes back that there are two kind of friction you are getting here. One, we are entering here, okay, the material when it is passing and when it is touching to the roll. And second one is when it is going out in either other side also you are getting some friction there. So here I mentioned that the angle between the entrance plane, you can see here, the angle between the entrance plane and the center line of the roll. The angle between the entrance plane here, okay, and to the center line, whatever the angle you are finding, that angle is known as the angle of contact. Okay, so here we mentioned this is alpha. So when the stock, the first, the angle of contact, this is clear now. The angle between the entrance plane and the center line, whatever you are created or creating by the roll, and this is known as the angle of contact or alpha. When the stock first contact, whatever the material you are putting here or you are using in the rolling mill, first contact the rolls at the point x dash. So initially, in this point actually you are putting here the upper roll you are putting here at x point, or it is touching at x point, or the bottom roll it is touching at x dash point. And the forces exerted by the roll, what kind of forces actually you are generating here by the roll on the stock at the entry plane are the radial force PR, because you are getting two forces here. One, this radial force you are getting here, that is known as the PR here we are making P radial, and the tangential frictional force, whatever the frictional force you are getting or you are generating here, this is known as the frictional force F, right? Two forces you are getting. And the horizontal component of PR, radial force, whatever the horizontal component force, the PR you are getting here, because this is important, because this force you need. Okay, so one force, the F actually, it is going towards in this direction. So this is because this angle is alpha and this is 90 degree. So this is known as the F cos alpha, because what we have done, if this is a triangle and this is 90 degree, and this value will be F cos alpha and this value will be PR sin alpha. Okay, so probably we'll put in this equation here. But before that, just I want to tell that the horizontal component PR or the radial force acting away from the roll gap tends to reject the material. So that means initially here, what the system will behave. The system will behave that you will make some friction here, or you will make some the parallel force here, so that it will reject the material. So that means it will not allow to prevent there. It will not allow to pass there. So that means it will prevent it from entering the rolls. Okay, it will not allow to enter there. While the horizontal component of F friction, the horizontal component, it will acting towards the roll gap at the entry plane tends to drag the material. So that means this F force, okay, the horizontal force, it will act to drag the material from the left hand side to the right hand side. Okay, so there is two meaning. One is it will make a obstacle there, or it will find some the bar there or the hindrance there, or the second one, it will try to drag the material from one side to another side. if the front face of the stock at the plane of entry is located at an angular position, whatever the angular position we have or the angle of contact we have, if from the line joining the roll center, the net horizontal force. So now you have two forces. One is PR sin alpha and one is F cos alpha. So what will be the net force? So net force equal to H equal to F, because this is in one direction and this is opposite direction. So this H equal to F cos alpha minus PR sin alpha. Right? Is it clear up to now? Yeah.
Yes, sir.
Okay. So now when
Yes,
the
sir.
force, now when the force H is positive, because now two things are there, because every time we have to think that whether if the force is positive or if the force is negative, what will happen. So when the force H is positive, so that means when this F force will be positive, the workpiece moves in the forward direction. It will go back, or it will go to the right hand side, or it will go in a normal path. But when the force is negative, the stocks moves backward. Okay, so that means if the force or the the outward force, if this is lesser or this is negative, then the the material cannot pass, so it will go back or it will come back. Therefore, the condition under which the rolls can bite the workpiece and unaided rolling is possible. So that means your H should be more than or greater than equal to 0. So that means H should be greater than 0, because if it will be 0, then it cannot pass. Okay, so in the normal condition, you have to think that H should be more than 0 or maybe equal to 0. So that means F cos alpha, whatever this equation we have, so F cos alpha is greater than or equal to PR sin alpha. So that means this force, whatever the F cos alpha force is there, this force should be greater than PR sin alpha, okay, or equal to sin alpha. Two things are there, right? Okay, so if this is clear, so now two things are there. One is we talked about H is greater than 0 or equal to 0. So now we have to find out the limiting condition. What is the limit? Okay, above that you can go or it can pass. So the limiting condition for the unaided entry of the workpiece into the throat of the roll is H equal to 0, because we have to consider the minimum. This is the limit condition. If we'll consider that H is less than 0, then it cannot pass. Okay, so that means there is no limit. So the minimum one is H equal to 0. So the moment H equal to 0, so that means F cos alpha equal to PR sin alpha, what we have done already. Okay. So now if you will follow the Coulomb's law, whatever also we have done equal to D max equal to mu square R. Similarly, if we will follow the Coulomb's law of sliding the friction, we have this equation F equal to mu PR, where F already we have derived that one is the rolling force and mu equal to the coefficient of friction. Okay, and PR equal to this force you have. Okay, so F by PR equal to mu, right? So now we have to understand that if the workpiece cannot be drawn into the row, okay, so that means we have tan alpha is less than or equal to mu. So that means if we have this angle or the tangential angle or tangent angle of the alpha, if this is less than or equal to mu, so that means it cannot pass the roll from the left hand side to right hand side. So what we have to do? We have to take the minimum one. So minimum means, for example, it will be more than mu. So that means what we have to do? Tan alpha equal to mu, because this is the minimum. Okay. So we have to make tan alpha max. So this is known as the tan alpha max. That means this is the minimum one, and this equal to mu. And whereas this alpha max, because initially we talked about the angle of contact alpha. But now if this is alpha max, this alpha max is known as the angle of bite or the gripping angle. So there are two differences now. One is the angle of contact. This is normal angle, which is created by the initial touch point of the roll to the vertical line or the center line. This is known as the angle of contact. Now, when you have the alpha max, this angle is the minimum. Okay, in that point, you are calling this is alpha max, and this is known as the angle of bite or the gripping angle. Right? Is it clear? Fine.
Yes, sir.
Okay, so now based on this, so I have only prepared a small numerical, only small one. Just you can do by yourself. Then I will show. This is the question. Determine the maximum, because we have not done based on this the angle of contact. So determine the very small one. Determine the maximum possible reduction of cold rolling a 300 mm thick slab when mu equal to 0.08 and the roll diameter is 600 mm. What is the maximum reduction on the same mill for hot rolling when mu equal to 0.5? Have you understand the question? So what is given here? So initially the thickness is given. Okay. So maximum possible reduction for cold rolling at 300 mm thick. So that means T0 is given, right?
Yes, sir.
30 millimeter. Then friction is given. But how much is friction? Mu
0.08.
0.08, right? Then you have to, and the roll diameter is given. Capital R is given 600 mm. So you have to find what is the maximum reduction. So that means D max. Please try. This is the very easiest one, very small. Who has done? Anybody done? Hari Prakash, Guru Nishant, Johan, Sonal, so what is the angle alpha? Vishnu, Kiran, what happened? All became silent. 65 students, nobody is responding. Anirudh, yeah, Amal, what happened?
Yes, sir.
Yeah, you are doing?
Yes, sir. I'm just trying to fix. There's an audio problem, so I'm
Okay.
trying to fix that, sir.
Vishal, to whom I will call because nobody is responding. This is the easiest one. Dia, Aditya, no. So I will show or you will try. 1 minute I will take. Akash, good. Okay, so you can see. Okay, so in the two way actually you can do. Okay, so without alpha also you can do because whatever we have derived the equation, if you want to find out the D max, so initially you have to find out D max equal to mu square R. Okay, so mu is given 0.08, so 0.08 square into R is how much? The diameter is given 600, so R equal to 300. You will get 1.92 mm, right? then it is asking that what is the maximum reduction on the same mill for hot rolling when mu equal to 0.5. Okay, so instead of 0.08, if you will put in mu 0.5, so you will get a D max equal to 75 mm, right? So this is one part. And if you will do in other way, like whatever we have done in the angle of contact based on this, we can make tan alpha max equal to mu. Okay, whatever the equations we have derived just now. For example, if we go back this one, tan alpha max equal to mu. Then alpha max equal to, you will find out from here, because mu is given. Mu is how much? 0.08. Okay, initial, because this is the initial mu, 0.08. So you will find alpha max equal to 4.57 degree, right? So the tan alpha max equal to mu equal to this mu equation also, d by r to the power half. Okay, this equation already we have derived in the before classes. Okay. So now D we have to find out. So tan alpha max, instead of alpha max, you can put tan 4.57 degree equal to D by R. R is given 300. Okay. And to the power 0.5. So you will find D max equal to 1.92 mm. Okay. The similar one, the first part. If you will not do in this way, you can take the angle, then you can find out here. Right. Then also the other part, D max equal to mu square R. You will put in this similar equation, you will find 75 mm. Fine. Yeah. Is it fine?
Yes, sir.
Okay. So, these are very simple. You have to do by yourself. Okay. So, because we have done very big numericals, but now very small numericals also still you are not doing by yourself. Okay. Okay. Make a practice. These are, small things you can make a practice. Okay. So, next we have, is it clear or any question up to now?
No questions.
No question? Okay. Okay. Fine. So, now we will go for the problems in the defect. So, can somebody tell what kind of problems actually we will get in the rolling? Just guess and tell. These are, you
Sir,
can, yeah.
so the thickness may be not even.
Thickness may be not even.
Yes, sir. Like while rolling.
Yeah, yeah. Okay. Any other?
Cracks may form.
Cracks. Okay. So anyone, any other? No. Okay, fine. Yeah, all whatever you told, the cracks and the edges, these are also where cracks you will find, and also the edges also it will be not good. Okay, so apart from this also we'll find something. So I will derive in other way like that what kind of problems or the defects you are getting. At the same time, how you will solve this one, because we are not going detail like the generalized or the common statements we are just making here, because this depends upon the material or your system or your the environment, how you are working there. Okay, so everything that parameters you have to think. So a variety of problems in rolling related to specific defects can arise depending on the interaction of the plastically deforming workpiece with the elastically deforming roll and the rolling wheel. Okay, so three things you are considering here. One is the plastically deforming workpiece, because your workpiece you are making or the material whatever you are putting, these are we are considering as a plastic deformation because it is changing. So, and the rolls actually these are elastically deforming because these are not deforming. So that's why we are telling this is elastically deforming. And the third one, we have the rolling mill. Okay, so that also it will make some create, because sometimes you have two roll, two high roll, or sometimes three high roll, sometimes four high roll, sometimes cluster milling. Okay, so this depends upon the roll also. So under the influence of the high rolling forces and the rolls flatten and bend. So whenever we are talking about the forces, so that's why we are talking about what kind of forces actually you are generating there, and how you are deriving that the metal piece. Because for example, sometimes you are preparing or you are sending the soft material, sometimes hard material, sometimes the forces will be you are creating more or you are giving a lot of pressure there, right? And also the rolls flatten and bend, and sometimes also the material pills also it will be become bend, and at the same time also the rolls become sometimes flatten and bend, and the entire will be elastically distorted. So that means when the rolls you will have some problem. For example, if we'll see our the motorbike, sometimes the rim. Okay, so that one it will bend sometimes. Okay, the moment it will bend, then everything will be disordered, right? Because of mill spring, the thickness of the seat exiting from the rolling mill is greater than the roll gap. set under no load condition. So whatever we just derived in the angle of contact. So because of the mill spring, because you have a mill spring and the thickness of the seat, whatever the material you are putting, that depends upon the the mill spring. Okay, so these are all interlinked. In order to roll to precise thickness, it is necessary to know the elastic constant of the mill. So every time I'm focusing on the precise thickness, because you cannot tell that only I'm putting some material, then I will get some plastically deformed slab or maybe the seat. Okay, so you have to think very precisely, because this is a you have some width. Okay, so if you will not take precisely, then probably you will find somewhere some mistake. And this is usually whatever the elastic constant of the mill, if you want to find out, we are not deriving here, but this one normally you are using from the calibration law. Okay, so maybe for example, when somewhere we have a setup, let's say in company somewhere, they have some calibration curve. So this is already derived that one. So from that only you have to find out the elastic constant of the mill. Okay, for example, the elastic constant for most screwed loaded rolling mill is around 1 to 3 giganewton per meter, while hydraulically loaded mills may exceed to 4 giganewton per meter. This is some of the examples of that in the company data, whatever they have. This is company data, and this you are normally getting from the, or you are finding from the calibration curve, right? So now the elastic flattening of the rolls with increasing the roll pressure results in a condition where the rolls eventually deform. So now you told already we have the seat, probably the edges maybe you will not find in a proper edge, or maybe you will find some wavy kind of edge, and also sometimes you will make a crack or you will find some crack. So whenever we are how it is creating actually. So you are creating by increasing the roll pressure, because you do not know how much load it is required for this kind of material, for this soft material, or maybe for this seat. We do not know. So in that case, what will happen? You will find some the rolls also eventually deform, because we have normally in the rolling mill we have the material will deform, but in case of your roll will deform, then what will happen? So you will miss everything, you will lose everything. Thus, for a given material and set of rolling conditions, there will be a minimum thickness below which the seat can be reduced no further. So that means you have put a certain material, okay, and it will pass to other side, but it cannot reduce more. That means, for example, let's say if you have 10 millimeter of thickness initially, but it is going towards 4 millimeter, but after 4 millimeter you cannot reduce. So that means there will be a fixed condition there. It has already been seen that thinner gauge seat can be produced with a small diameter rolls. One more also what I told about the rolls. For example, whatever the small rolls sometimes you are taking, sometimes you are taking big rolls. If you remember that rolling mill when we have talked, small roll and a big roll. So also it is already been seen that the thinner gauge seat can be produced with a smaller diameter rolls. More complete analysis of the problem, so that the limiting thickness is nearly proportional to the coefficient of friction. Okay, all the parameters now it is coming. The limiting thickness, whatever the thickness you are preparing or you are fixing there. Okay, so that means this is the limit you have to prepare or you have to put there, is nearly proportional to the coefficient of friction, the roll radius, and the flow stress of the workpiece, and is inversely proportional to the elastic modulus of the roll. Okay, so based on this, we have already derived when we talked about the all the equations, and based on this, we have done the numericals, right? The roll gap must be perfectly parallel. The roll gap, that also must be perfect, because if you not make it parallel, then probably you will not find the proper seat flow. Okay, then also you will not find the the balanced material whenever you are taking out. Okay, so you have to make it the roll gap. It should be parallel. Okay, otherwise one edge of the seat will be decreased. So what I think Aditya or somebody was telling, otherwise one edge of the seat will be decreased more in thickness than the other side. Okay, so that means whenever you have a seat, so one side it will be thicker whenever it will come out, and one side it will be thinner. Okay, so you will not make it parallel, right? Is it clear up now?
Yes, sir.
Okay. Yeah. So there are two aspects to the problem of the shape of the seat. The first pertains to uniform thickness over the width and along the length. Okay, so that's how we derived initially the draft and then the reduction. Okay, so one is uniform thickness. So you have to make it uniform every time over the width and the length across the length. And this property of seat can be measured accurately, and it is subjected to precise control. Okay, so that means you have to think about the precise control. If you not think about, every time we are focusing, because whenever two things normally I am focusing. One is when we are talking about academics, we are just doing something. If we have some error, or if we are telling, let's say you need 2.005, but if you are getting 2.001, then you are telling, okay, this is acceptable. Normally we are telling in academics line. But whenever you are doing anything precise control, because now in academics you can make it, but whenever you are going to the company or somewhere, because this depends upon the customer. If the customer they are telling that you need precise of dimension of let's say 4.005, you have to do that one. Otherwise, they will again tell that you have to decrease the manner. Okay, otherwise they will not accept. And the second important property of a seat is the flatness. Okay, it's difficult to measure this property whenever we are talking about the flatness because it's a long seat. Okay, so that's why we are telling this is difficult. And also, if you remember, I told in the laboratory, normally the rolling and this kind of work is very difficult to because you need rollers and it should be very big. The equipment is very big. You need a big space, and whenever you are putting a seat, actually, you need a long space there. Okay, so it is difficult to measure this property. Particularly difficult are in a process measurements taken as the seat moves through a continuous wheel at a high speed. Okay, because it is continuously moving or it is continuously flowing at a high speed. So that's why it is very difficult. Or you need also a long seat it is moving. We are not thinking that only one, for example, 1 meter or 2 meter. Very long seat it is moving from one side to another side. And the rolling process is very sensitive to flatness. Okay, so whenever you are talking, you do not think that when a big equipment we have, so if plus minus something will happen, then we can manage. No, you cannot manage. Okay, so that's why you have to think carefully. A difference in elongation of one part in 10,000 between different locations in the seat can give rise to waviness in a thin gauge seat. Okay, so I will show some of these photos that you will see here. So if you are finding some the waviness or the lack of flatness, how actually it is generating, how actually it is creating that. Okay, so there is some schematic diagram you can see. We will find here. This is actually the lack of flatness. What you just told a few sometimes back. You will find this kind of seat. Okay, for example, if you remember, whenever we have some some paper, let's say we are putting on the table or maybe somewhere with the sticker or the gums you have in the bottom, if it is not flat, then you will find some gap inside. Okay, so then what we are doing, we are just pressing that on how it will go inside, but it will not, because other side it will be already pasted, right? This example I think we have done, or maybe we faced in day-to-day life. Okay, so you can see here, if the roll deflect, as in figure A, the first part, if the roll actually deflect, the edges of the seat will be elongated. So that what happened, because this is a material piece. Okay, so this schematic diagram. So in the material piece, this is the middle part of the material. Okay, and this is the outer side. If the roll actually deflect, roll deflect means if a roll will elongate or it will expand. So in that case, what will happen? So the both the side or the edges actually, these are we call edges. In the edges actually it will elongate, whereas in the middle of the sample or in the middle of the material it will remain same. So that means it will have no impact. Of course, it will be in one material sheet, but you have no deformation there. So the moment you have no deformation, you will find this kind of material, right? So that means the edges will be longer, but the in between will be smaller. Okay, so if the edges were free to move relative to the center, we would have the situation shown in P. Okay, so that means if the edges, if these are free to move, so that means you will find some elongated surface on the edges in the both the side, and center will be like this. Okay, however, the seat remains a continuous body and the strength readjusts to maintain the continuity. But what will happen? It will not stop here. Okay, whenever it is rolling, so that means this material will pass. This material will pass from one side to another side. But the other side, the both the side, it will be like little longer. So the moment you have longer, you will find this kind of the waviness or the it will be not flat. Okay, because this is already elongated here. Okay, so it will make to try to make balance with the middle part, but it cannot. The result is that the center portion of the seat is stretched in tension and the edges are compressed. Okay, so that means here you will try to find out compress. For example, the third part, you will try to find out compress here in the both the side because it is already elongated. So what he will do when he will try to cope up with the center, so that means it will try to make it compress. Whereas the center one, he will try to cope up with the edge also. So what he will do, the center part will try to tense or it will try to stretch one, so that the center part will find or it will try to cope up with the edges. Right? Is it clear? Yeah.
Yes, sir.
Okay, so finally the result will be the wavy edge or the edge buckle, this one, the D part. Okay, under other conditions of the strength distribution produced by the long edge could produce short zipper breaks or the cracks in the center. So whenever you have the strain distribution, so you will find some cracks. But somebody was telling about, you will find some cracks also inside. This is the part in the final. Okay, so these are basically we will find this kind of the defects actually in the rolling. So you have to be very careful about all the property, all the parameter before you are putting, because if, for example, you are getting, let's say, one seat or maybe one piece you have just only entered there, but you will find this kind of output after the rolling, then what will happen? So therefore, before going to the beginning, you have to study all the parameter. You have to think about all the property of the material or the the structure. Then you have to pass the material. Okay. Yeah. So also I mentioned here the solution to roll bending is to contour the roll parallel to its axis, so it is larger in the center than at the ends. Okay. So one more thing, if whenever you are finding the roll bending, okay, whatever the initial what we have talked up to now, so that means if you have the roll is not in a proper position, or maybe you have some deformation of the roll actually you are getting, then what you know, you have to make the roll parallel to its axis. Then only you are finding the solution, because we are not finding only the problems. So as an engineer, we have to give the solution as well. Okay, so if you have the question of roll bending, or if you have the question of or the defect of roll bending, then this is one solution, that you have to make the roll parallel to its axis. Then when the rolls deflect, they will present a parallel gap to the wall. So that means whatever the gap you have between the two rolls, that gap should be uniform, or maybe it should be parallel. If you have something plus and minus, one side is little bigger and one side is little smaller, that gap I am talking, then you will not find good. Rolls having a ground camber or the crown are usually used. So sometimes what happens, so we are using, for example, how to say, when you are drilling a hole, hole in the wall. So we are putting a the plastic kind of material or maybe the wood material inside. Okay, so that means we are giving some support so that it can keep in a stronger position. So similarly, also the rolls whenever we are putting, if this is not proper, so also we are making or we are giving a ground camber or maybe crown to that one, or maybe to give a support. And this produces suffer from, and camber can also be produced thermally due to thermal expansion. So one more thing also, we are adding sometimes there, or we are giving a support to there, and also at the same time, so sometimes whenever we are making the rolling, the camber actually they are producing by themselves due to the thermal expansion. Okay, why? Because you are generating temperature there, and the moment you are generating temperature, the temperature difference is there, then also automatically it is created there. And this procedure suffers from the fact that the camber corrects from the roll deflection at only one value of roll force, and it may not be effective measure for a range of rolling conditions. So that's why this one is also not good, because sometimes if you are creating their camber by by the thermal expansion, maybe after some time again it will decrease, right? So that place again it will vacant. So this is also not a good solution to give this one. So you have to think, if for example this A is not good, or the A path is not good, or the A solution not good, then I have to think about solution B. So a better technique is to equip the rolling wheel with the hydraulic jacks, which permit the elastic distortion of the rolls to correct for deflection under rolling conditions. So that means you have to give a hydraulic jack there, so that whenever it will make a deflex, so that means the jack is there, or the hydraulic the system is there, so that it will adjust there. Okay, and the suggestions for a rolling mill with flexible rolls. So one more thing is also they are suggesting that if you want to make a flexible roll, for example, if automatically it will make a a small roll if it is necessary, then you can also extend. Because why? What happened? Sometimes in the rolling mill, in the two high roll mill, let's say, if we are using the bigger roll, we cannot change to a smaller roll. So if you have the flexible roll system, so instead to remove that old one or the bigger roll, we can put the smaller roll there, or maybe we can add also another two rolls, we can make it four high roll mill, right? So these are some of the options you have, so that you can correct it, right? Is it clear? Yeah. Yeah, so the last part actually we will just talk about the crack, because you told about the crack also. So the problems with shape and flatness are brought about by inhomogeneity in deformation in the rolling direction of the seat. Whenever you are finding the seat, or whenever you are creating the seat, you are finding inhomogeneity. Okay, whenever inhomogeneity in deformation. So when you have the inhomogeneity in deformation, so you have to find out the crack there, okay, in the material. Okay, so this thing already we have talked about. So if the outer edge, if you want to find out to stretch it, or maybe inside, the middle part or the center part, you have to compress it, then you will find a lot of the distortion there, or a lot of the imbalance there. Okay, so if you have some imbalance, then only you will find some cracks here. Okay, so I mentioned here because there is a continuity between the edge and the center, the edges of the seat are strained in tension, a condition which leads to edge cracking. The moment you have this kind of imbalance structure, or somewhere it is trying to make it tension and somewhere it is trying to make it compression, then you will find some edge cracking. Okay, edge cracking, not the center cracking. Under severe condition, because center cracking we have discussed in the previous slide already. Under severe condition, the strain distribution shown in figure A can result in a center split. So when you have a lot of cracks there, now when you are applying the severe conditions or the extra condition, then you are finding the center split. Okay, because you can see here. So this side is now trying to tense or maybe stretch it, but inside it is not trying to, it is trying to compress it. So you will find this kind of shape, or we call this a center split of the seat. Right, fine. Because sometimes in paper normally when we are making, sometimes you will find when you are stretching, you will find some cutted there, or maybe automatically it will tear. Right, is it clear?
Sir, could you tell the difference between edge and the center cracking once again?
Which one?
Edge and the center cracking.
The B and C.
Yes, sir. Yes, sir.
Yeah. So what happened, for example, what I told in this slide, let's say, the material piece you have. Okay. So whenever the material piece you are putting to the rolling mill, so the center part, the outer side, both the side, both the edges, let's say, this is the edges. Okay. So this is the upper edge or this is the lower edge. So here actually it will be little elongated. Okay. Why elongated? Because your roll is deforming, or maybe the roll gap is not similar, they are not uniform there. So this outer part actually, or the outer edge, it will try to make balance with the inner part or the center part. And the center part, what he will do, the center part will try to cope up with the outer part. The moment that they have with a different of the aim or different goal, then you will find outside cracks are there, or outside some edge crack are there, not the inside crack, outside edge crack are there. And the moment you have a lot of edge crack, and when you have a lot of the strain difference or the strain distribution, after long time, after propagation of the crack, then you will find some center split. Because what will happen, the center, the outside edge or this side edge and this side edge, it will elongate it, but the inside one is stretched, or this is compressed. Similarly, also sometimes what happens, the outer part will be try to compress, but the inner part will try to stretch. Okay, so in that case, you will find this kind of tear, or it will try to separate from the center one. It will find to be alone, and also it will find to be alone from the center part. Right? Clear now?
Yes, sir.
Okay. Yeah. Okay, fine. So I think one more also the same, in the similar way also we derived in other part also. Edge cracking also can be caused by inhomogeneous deformation in the thickness direction, what we just told. And when the rolling conditions are such that only the surface of the workpiece is deformed, the surface of the workpiece. Okay, so you can see here. So that means in other way, if we can find out, that means the surface of the workpiece is the upper part. This is only deformed, but inside is not deformed. So that means you can see when this is deformed. So that means this is elongated, because we are talking about, if you remember, our thickness is decreased, but width is increased. The moment you have width is increased, you can see the upper part is deformed already. So that means width is already increased, or this is elongated, and this the lower part is also elongated because two rolls are there, but inner part is still like this. Okay, so that means the surface of the workpiece is deformed. Okay, so in subsequent passes through the rolls, the overhanging material is not compressed directly, but is forced to elongate. So what I just explained, okay, so this is already elongated, but this middle part, it is trying to elongate. It is trying to cope up with the upper part, but this is still not working well. That means it is trying, but it cannot do. With a heavy reduction, the deformation extends through the thickness of the seat. The center tends to expand laterally more than the surface to produce barreled edges similar to those found in offsetting cylinder. So that means when we have heavy reduction, okay, so that means initially we have applying a lot of pressure there. Okay, so heavy reduction, so you are finding this kind of structure immediately. With a heavy reduction, that the deformation extends through the thickness. Okay, whatever the thickness we have, whatever we are passing. So initially, instead of this one, if we are putting the heavy reduction, we are getting directly like this. Okay, but this is not required, but we are putting a lot of pressure there, or a lot of roll pressure there. So you are getting this kind of structure. And also one more thing, we have some stresses generating there. Okay, so initially when we derive the equations, I told we have a lot of stresses, but at the same time, also we have a lot of secondary tensile stresses we have. Okay, so here actually it is mentioning, and the stress distribution also extend in the rolling direction, and if there is any metallurgical weakness, so when we have the stress distribution, so we will find some metallurgical weakness there. Okay, along the center line. Okay, so whatever you have, whenever you have some weakness in the material piece, so you will find this is known as the alligatoring. Okay, so that means this picture you have the light reduction, so that means low pressure you are giving. The moment you are giving the high pressure, you are getting this is heavy reduction, and the third one you have the alligatoring. So that means you are getting some metallurgical weakness there. Okay, so the material you have somewhere you will find some weakness. The moment you have weakness, we will find this kind of structure. So the alligatoring type of fracture is essential if there is any curling of the sheet because one roll is higher or lower than the center line. So that means if you have the roll gap, whatever the roll gap between the upper roll and the lower roll, if this is not uniform, then you will find this kind of structure. Fine. Okay.
Yes, sir.
Yes, sir.
So this is the last slide we have the defects on the other than crack. Also, you are finding some internal defects. Okay, so for if you have some internal defects, we are calling this fissures are due to incomplete welding of pipes and the blowholes. Okay, so that means if you are creating some blowholes, welding means do not think that whatever the joining we are making. Okay, incomplete welding of the pipe, whatever the pipe or the material piece what we are making, you are creating some blowholes. And how you are creating the blowholes? If you have some air bubble inside. Okay, so if you remember, we talked about forging. If you have some the inside gap something, or maybe if you see somewhere on the metal piece when we have machined, some of the bubbles you will find on the upper part. Okay, so that's why with the help of some gases, then you are finding some blowholes. So that these are known as the internal defect. Okay, so some also apart from this longitudinal stringers of non-metallic inclusions. Okay, if you have some impurities also non-metallic, so that means non-metallic part, but these are attached as some inclusions there, or maybe if you talk in a technical term, this is known as the pearlite banding. Okay, in steel normally, so that's why I'm telling it depends upon material to material, and these steels are related to melting and the solidification practice. So that means whenever you are solidifying that one, so what I told every time you have to increase the temperature, then holding time, then cooling time. On solidification means you have to make the cooling time. So that will much more impact because you have to cool it with certain temperature. You cannot take that. You have to cool it maybe in water bath or maybe the oil bath. Okay, it depends upon material. If it needs actually for the water quenching, then also you can. But otherwise, you have to go slow furnace cooling. Okay. Then also I made it here how actually you are removing the surface defect. So in order to maintain high quality, the surface of billets must be conditions by grinding. Okay, so what we have done already in the machining actually, conditions by the grinding, chipping or burning with an oxygen lens to remove the surface defect. Okay, if you have any surface defects such as the silver seams and scabs, you have to remove with the help of the grinding, chipping, or maybe you have to burn with an oxygen lens. And also if you have scratches, the scratches you are actually getting due to the defective rolls or the guides. If your rolls are also defective, if you remember, I think I do not know whether maybe Charles actually was doing, he bought a cutter actually. So in that cutter, when he was cutting, he found a crack there on the the grinder tip. So the moment you have grinder tip or the roller tip is somewhere scratches, so that scratch also it will deflect in the material piece. Okay, so that also you have to remove. Sometimes problem arise with removing the rolling lubricant or because of the discoloration after heat treatment. Okay, whenever you are removing the lubricant, the rolling lubricant what you are using, that also it can arise to crack or maybe to make some other problem to the rolls as well. Okay, and also one more is the heat treatment. After heat treatment, if you are checking whether you are the cooling structure is not good or maybe the cooling cycle is not proper, then also you will find some defects. Okay, so if you have any question, you can just ask. We have covered all the rolling defects, so I think you have understood